I'm talking about, she said, the role of windage in the North Atlantic circulation. This has to do with my project I've been working on about Sargassum for a while, but this is just the portion of it that had to do with the windage subject highly. So the collaborators on this particular talk are Rick Lumpkin, Nathan Putman, and Ryan Smith. There are more co-authors on the bigger paper, but these are the ones who have contributed work into this talk. All right, you've heard about the Sargassum in the Caribbean problem. That's on the left, floating Sargassum in a single clump, the upper panel, that's one group of one plant, and rafted in the lower panel like it is usually found. And as it started to be found in 2011, Sargassum actually closed a resort beach in Antigua in 2011. It was so big once it piled up, and when Sargassum piles up deep like that on the beaches, it sits in the sun and it smells, and the tourists won't go in the water, and everybody loses money. So, and how unusual was this? This is based from the Maris satellite maximum chlorophyll index that was published by Gower et al. 2013 and Brooks et al. 2018, and were provided to me by Maureen Brooks. This is computed in the 10 to 20 degree north latitude band for the Eastern Caribbean, which is shown in gold, the tropical Atlantic between 60 and 50 in red, and 50 and 40 in blue. And I think it's fairly obvious from there that it's unusual to find Sargassum. This satellite MCI directly tracks Sargassum, the qualities of Sargassum being that it hangs together in large rafts and for a long time, as opposed to blue-green algae things and other kinds of little blooms you can find. So there never was any before, pretty much. That's what the people report too. Big spike in 2011, and then some in 2012, and there was a hiatus in 2013. And this is not pertinent to my story, but it has increased again. It's thrived in the tropics, and other complications have happened. And so 2018 was probably the worst year ever down there. And I don't know whether maybe the Sargassum on the beaches here is related to that or not, because we are downstream. So anyway, now we're going to mostly talk about winds and currents, now that you know why. All right, motivation. Prior to 2011, it had only been observed in the Sargasso Sea and its upstream source in the Gulf of Mexico. But starting in spring 2011, it began arriving in the tropical Atlantic and inundating the Caribbean Sea, causing negative economic and societal impacts to the fishing, diving, and tourism industries. And surprisingly, around the same time, a similar phenomenon was affecting the coastal areas of West Africa and equatorial Brazil. That was not what was expected. At this point, people just assumed that it was coming from the Sargasso Sea southward, and what on earth is happening? Is it global warming or something big? So the general public and the scientific community were very interested in why this was happening, if it would be ongoing, and whether it could be predicted ahead of time to aid in mitigation efforts. But scientific studies using drogue surface drifter trajectories and numerical models to backtrack the surface currents from the Caribbean in order to identify the origin of the Sargassum mysteriously were not able to find a connection to the Sargasso Sea. Its origin appeared to be in the tropical Atlantic and possibly the South Atlantic, areas where Sargassum had never been seen before. But I was sort of stubborn, and I just started out thinking it had to come from the Sargasso Sea. But this study revisits the possibility that the Sargassum did originate in the Sargasso Sea, and that this can be shown if windage and the big negative North Atlantic Oscillation, NAO event, of winter 2009-2010 are taken into consideration. That's the longest word slide on it. So, okay, the order of the talk will be talk about the climatological winds and currents of the North Atlantic briefly. I think you're all pretty much expert in that. The North Atlantic Oscillation, same thing. The NSEPRI analysis, winds and surface currents, when I try to look specifically at climatology and at the event. Then some surface drifter analysis that Rick Lumpkin helped me with. And some HICOM ICTHIOP, that's a particle tracker that goes with HICOM, numerical model experience that Nathan Putman helped with last fall, and that turned out to be very enlightening, especially because none of the other methods can truly get at with enough data interannual variability where you look at a specific event and see what it did. So let's do it. This is a map that Rick had generated from satellite winds, climatological winds over the North Atlantic, showing the westerlies, the trade winds, and the strong southward winds off Gibraltar and West Africa. I want you to really notice those. They'll become important for the story. The location of the intertropical convergence zone migrates seasonally to the north during the boreal summer and to the south during the boreal winter. And that's just what it does, but it affects the surface currents in the tropics also, so that's significant. Can everybody hear me okay? All right. This is a map that Rick also made of the climatological surface currents of the North Atlantic from surface drifter average trajectories. These are drogued drifters, showing the Sargasso Sea, the major currents forming the subtropical gyre, and the currents from the North and South Atlantic that comprise the tropical Atlantic current system. The tropical currents vary seasonally, especially the NBC and the NECC. If you need me to stop at any point and explain those, we can, but I think we're all pretty well versed in the tropical Atlantic circulation. And you know that the main seasonal variability down there is that the North Brazil current periodically, mostly in the summer, turns offshore and becomes the retroflex and flows into the North Equatorial countercurrent, which then flows due east and actually all the way into becoming part of the Guinea current. But during the springtime, late winter and spring, the NBC stays straight, flows straight up on into the Guyana current and the Caribbean current and the whole loop current system. So that's a very interesting place to study for that reason alone. The North Atlantic Oscillation, these are just some long-term time series of the annual averages of the index. The annual average is shown in the left panel from 1895 to 2017. And as you can see, calendar year 2010 was the most extreme annually averaged negative NAO event since the record began in the late 1800s. That's a real whopper. And you can see the monthly values in the other one from 2008 through 2017. You can see 3 negative NAO events. The first one is the one we'll mostly be talking about today. It was in December 2009 through the end of March 2010. There was another one at the end of December, end of 2010, I mean, in December of 2010. That was a resurgence phenomenon where it was triggered by the first one, and then the summer temperatures warmed at the surface and it came back out. And there was another independent NAO negative in March 2013. But what was noteworthy of the first one was its 3 to 4 month persistence as well as its extreme values. Though it's the persistence that led 2010 to be the biggest negative annual average. Among other effects of the NAO, a negative NAO causes the westerlies to strengthen and move south, as we will see in the next slides. All right, first we'll talk about the NCEP reanalysis results. I'm going to talk about the wind fields and the surface current fields, and then both of them with a 1% windage correction applied. Windage, most of you know, is a direct effect of wind forcing at the sea surface on floating and partially submerged objects, such as drift cards, buoys, oil spills, derelict boats, etc. Empirical studies have shown that windage is generally 1 to 3% of the surface wind speed in the direction of the wind. And the hypothesis underlying this particular analysis is that Sargassum will fall into the range of 1 to 3% of windage, and that will affect its movement compared to the surface currents. For this project, this time we chose the most conservative 1% windage to apply, just so we could visualize what the change is if you were a partially submerged object, what you would experience. Now, this windage effect is in addition to the underlying Ekman and geostrophic currents and to Stokes drift, water particle motion caused by waves and swell, although it is sometimes used operationally to model both processes, kind of a proxy. It's easier to get a wind data set, a proxy of windage plus Stokes drift. But in this case, let's just see what happens if we apply 1% of the wind to known currents. Okay, this is just the winds. The climatological winds defined in this case for 2008 to 2015, just so we bracket the event. And in the upper panel, and note in particular the winds in the 20 to 40, 80 to 10 west band, the rectangle, which encompasses the Sargasso Sea, shown as a black oval for reference. And so we're going to be making some averages, doing some things with that rectangle. Now, I wanted to say this is just the nominal Sargasso Sea oval, just so you can see something on each of the maps. But the winds and the currents and everything that we look at leads me to believe that the real definition of the Sargasso Sea would be an elongated sort of ellipse going angled up to the northeast and going farther than that oval is shown, but that's the official Sargasso Sea. Now in the lower panel, the westerlies are stronger, as you can see, and located more to the south than the climatological winds. In addition, the east-northeast winds continue all the way to Gibraltar, to a certain extent, you can see there. Whereas in the climatological map, the winds there are southward. So that's what I really want you to compare between the two. And the trade winds are also weaker and are shifted somewhat south during JFM, January, February, March 2010. I just was looking at quarterly values of various things at one point in this, so I just chose to define the NAO anomaly as JF, and December, January, February, March would be more accurate, but this worked out just fine, and I also looked at the other. So, all right, here's the wind anomaly. Some people like to see the anomaly. This is the difference between the 2010 JFM and the climatological JFM. You can see the biggest differences are in the northern half of the domain, where the westerlies are clearly strengthened in the latitude band of the Sargasso Sea, which doesn't normally have the westerlies, and weakened where they are normally located north of around 40 degrees north. And noteworthy to say that everywhere else in the tropical Atlantic, the winds are very close to the climatology, so this anomaly affected only the upper part. And this is what the winds look like in a time series. The red is the climatology, and the monthly NCEP winds, blue, these are all averaged over the same 20 to 40, 80 to 10 band. And notice where the zero crossing is there. The climatological winds are generally weak and to the west, negative values, whereas in the three strongly negative NAO events, the direction is reversed and the winds are strong and to the east over the entire band. So that's just what it looks like in the time sense. Now the currents that are largely driven by the winds and the rotation of the earth and other physics there. These are the average climatological JFM currents in the upper panel, what it normally looks like, and the anomaly winds in the lower panel. In the climatological map, the center of the subtropical gyre is located at about 25 to 30 degrees north. You know, it's in the middle of, it's sort of low winds and low currents in the middle of the Sargasso Sea and all the way nearly across the Atlantic. And it is shifted to the south during January, February, March 2010, such that if you were to look closely at those little arrows, your magnifying glass, you would see that most of them, instead of being a circulating, rotating system, it's almost all pointed in some way to the east. So, all right, everything has had 1% windage added to it now. Climatological in the top and the NAO anomaly in the bottom. In the climatological map, the center of the subtropical gyre, the dark blue tones, is located in the normal place, whereas it's shifted to the south during JFM 2010. Everything is kind of accentuated, sort of stronger and almost well organized now that you've added the windage, which simply meant for every grid point adding 1% of the wind velocities, which are, as you know, much higher than the current velocities, adding 1% of that to the currents and then seeing what the resultant is. So this is the currents, inferred currents kind of that would move, partially submerged and floating objects that are subject to windage. People also use windage corrections to do things like larval transports and things. That's a little more complicated. It's probably getting into the Stokes drift and other types of forcing issues there, but Sargassum is big and sticks partially above the water. And not only that, but Sargassum has been observed many times and written up in papers, observed blowing onshore and strong onshore storm winds all over the Atlantic and Caribbean and Bermuda. And so people just eyewitness reports that it definitely is blown by the wind. Which windage can also, it's interesting, it doesn't have to go in the same direction as the currents. It can go counter to the currents or anything, whatever way the currents are going and then the wind is blowing. So note that the flow near Gibraltar, this is the best example of this now. This is flow, not the winds. The current with 1% windage, which feeds the Canary Current, originates in the 30 to 40 north latitude band during 2010, whereas in the climatology, it comes from north of 40 degrees north. This is an important difference relevant to the Sargassum story because traditionally the Sargassum is most densely south of 40. So, but it does probably take excursions in the circulation up and around too. And this is just what the time series looks like of the currents with 1%, 2%, and 3% windage applied. You can see it makes a big difference. The black is the current with no windage on the same scale as the 1, 2, and 3%. So it's a big effect. When the wind is blowing strongly, like during the 3 NAO things, it actually reverses, its sign. So let's see. Okay, I think we covered that pretty much. Now we're going to move on to the surface drifter results. Rick Lumpkin is not here today, is the head of the surface drifter program and has been very interested in looking into also drogued and undrogued things when we started talking about Sargassum, and he made a couple of targeted products for me that are going to be useful for this. First, we'll have a photo and characteristics of a surface drifter. We'll have average surface circulation of the Atlantic from drogued versus undrogued drifter data. Results from a statistical model of drifter probabilities from the entire drifter data set as it stood at 1979 to 2013. He's probably going to update it, I'm sure. And selected individual drifter trajectories illustrating various aspects of the surface circulation.
Can I ask a question?
Yes.
The surface current that you showed for the climatology and for 2010, was that a satellite product plus techno transport?
Which one? Not the UNCEP one. The first one.
Maps that
you showed. No, that's climatological and only climatological, and then only climatological currents, winds and currents. Just. No, the first two were from satellite and then from the drifters. The very first two at the beginning, you might not have been here. I'm not sure.
No, not the one that kind of, I think, previous one.
At the very beginning.
Why don't you go to the picture? Yeah.
1%
Okay.
Windage thing. That one.
Okay. That's from NCEP, and that's 2008 to 2015, January, February, March, and the same for just 2010.
NCEP ocean reanalysis, probably.
NCEP NCAR reanalysis, right.
Plus the drifters or
No drifters.
Just
No drifters in this at all, but what I was talking about was at the very beginning of the talk. That was from satellite, and that was from drifters. And now we're going to return to the drifters. First of all, there's Rick with a drifter to show you the size and everything of a drifter with a drogue. And Rick gave me the information. Drogue drifters closely follow the currents at 15 meters, more like nearly neutrally buoyant oil suspended in the mixed layer. Undrogued drifters follow a combination of wind, waves, and currents at the surface, more like positively buoyant floating debris, or sargassum. And the motion of an undrogued drifter relative to a drogued one is 1 to 2% of the wind speed. So our rough estimate of just a windage factor to be applied works very well if I were trying to simulate the movements of an undrogued drifter or other buoyant floating debris. It would be a good way to do it, and it's done. Lots of people have done that type of thing in the literature about various tracking and everything. So, all right, now here we are. This is similar to the second figure, except that now it has been divided. Rick has divided it between the mean speed of drogued drifters in meters per second and the mean speed of undrogued drifters. Now, at the first glance, you see certain things that are the same in both, obviously, the Gulf Stream, the tropical currents and all. But the current speeds from drogued drifters are generally weaker than those obtained using undrogued drifters and show striking changes in the location and directionality of some of the currents. This is especially evident in the Northeast Atlantic near Gibraltar and in the Canary Current and the NEC. As you can see, you could see the whole North Atlantic Current and then the Azores Current, the Canary Current, and all that darker blue then is the NEC feeding into the around the subtropical gyre. And it's hard to see, but it accentuates the, especially evident there. And the eastward turn around the Guinea Dome, which is that whitish area near 10 degrees north, into the NECC and Guinea Current right under Africa, is stronger, as is the eastern South Atlantic inflow to the SEC. You can see the whole South Atlantic has now gotten much stronger with windage and feeds into a stronger set of SEC currents coming up. And ultimately, that feeds into the North Brazil Current and the Caribbean, all of which is stronger in the undrogued than drogued map. Okay, now we're using a statistical model that Rick has developed that with drogued and undrogued separated, whereby he uses the big data set and looks at the probability from one grid point to the next of where drifters have gone in the past. Now, that includes inherently seasonal variability because it's all of the drifters and everything. So if there's more than one pathway, it will be reflected in the probabilities overall. But what it doesn't do is interannual variability. Maybe someday it will, but it doesn't. But we have a workaround for that when we get to the HICOM model results. So, but these are very interesting. You can see the drogue drifters in the upper panel have a limited set of pathways. Oh, these are the pathways to enter the Caribbean shown in black, those grid points. It's a 1 by 1 degree model. After passing each point, what is the probability that a drifter who was in one of those points would get to the Caribbean? And the scale is on the right-hand side. There's just a relative scale of 0 chance to 1 is you made it to the Caribbean. So they have a limited set of pathways from the east, and the longer pathway connects to the South Atlantic. But with windage, undrogued drifters have a different looking pattern. In addition to having a stronger connection to the eastern South Atlantic, they also have a much more clear connection linking the eastern tropical Atlantic and the Canary Current region to the north with the Caribbean. So now we have inflow coming in on the average from the northeast Atlantic and from the south. And you notice a little hot spot down there in the southernmost place. That was interesting to both Rick and me. We didn't, but I think that just has to do with the fact that if you look at the currents even farther off this map, you can see that it's a narrow, strong current coming there. It's all over to the east. And if you come into this domain there, you are basically going to go into the Caribbean. So you might spend some time going back and forth in the tropical Atlantic circulation, which doesn't show as much in this picture, but ultimately all roads lead to the Caribbean, and they also do from the north. So there's significant inflow from north of 20 there coming in, and if you find yourself in the western tropical Atlantic, you're certainly going into the Caribbean or just up along the Bahamas. So that's a very interesting difference between the two. It brings you a whole new pathway from the north. All right, now I know you can't. You're just supposed to look at broad patterns in these little maps, and I'll tell you what we have here is statistical backtrack drifter locations from a start point in the Eastern Caribbean. The drogue drifter results are shown in the left panel and undrogued in the right panel. At the time scale, can you read the time scale at all? It's 0, 30 days, 90 days. Can you barely? Okay. At the shortest time scales, 30 and 90 days, the drogued and undrogued drifter maps are very similar. Inflow to the Caribbean comes from the western tropical Atlantic, but by
undrogued is on the right.
Undrogued is on the right, yes. So they look almost the same. Drogued over there, undrogued here. You move along, they're a little bit different. But then by 270 days and beyond, however, the drogued drifters are still arriving from the tropical Atlantic with some input from the southern Sargasso Sea, some local sort of input. By 270 days and beyond, however, the drogued, they're arriving the tropical Atlantic now all the way across the basin, but more from the western side and from the Sargasso Sea, sorry. The undrogued drifters, on the other hand, are showing another major source of input to the Caribbean from the northeastern Atlantic. You can see it creeping up as 30 and 60 days go by, up the north side, from Gibraltar southward along the coast of Africa, and from the eastern South Atlantic as well, with the hot spot still at around 10 degrees south, which is there all the way to the end of this year and a half. Now these are a slightly different thing. Now look in the upper left one there. You see a little dot there at 16 degrees north, 20 west in the Canary Current. That happens to be where we'll see more clearly in the drifter trajectories, but that's a little crux point where flow either heads along the top of the Guinea Dome over into the NEC and in towards the Caribbean, or it can equivalently from the same point go around the Guinea Dome, flow under Africa, and then become part of the back and forth recirculating tropical circulation, and eventually into the Caribbean also. So we started the tracer right there at that point, and then wanted to follow and see what would happen for 10 years. It's not a tracer, it's the drifters, but it behaves like a tracer. It was forward track for 10 years. After 1 year only, the undrogued drifters have spread all the way across the tropical Atlantic and into the entire Caribbean and Gulf of Mexico and northward along the U.S. East Coast. That's very interesting. That happened rapidly. They diverged kind of, and you can see undrogued creates a far stronger pathway and fills the Caribbean with the yellows and reds and oranges. With time, the undrogued drifters tend to remain north of the equator, while drogued drifters eventually spread into the South Atlantic. The accumulation in the tropical Atlantic persists in the years 2 and 3 much more robustly than for the drogued drifters. The undrogued drifters are also less tightly confined to the subtropical gyre, escaping it to the far northeast much sooner after only 2 years than the drogued drifters. But I don't think it shows as much in these pictures, but ultimately the undrogued ones with the wind forcing contains everything more tightly into the Sargasso Sea, into the subtropical gyre, I mean. But so, all right, now we'll switch to some drifter trajectories, go fairly quickly through these. These are selected ones chosen to illustrate various aspects of the circulation related to the NAO wind anomaly and the possible pathways that Sargassum may have taken to reach the coasts of West Africa and Brazil, as well as the Caribbean Sea in 2011. We'll take a closer look in the next slides. Okay, I'm just going to pick from that same picture. I made them all go gray, and I'm highlighting a few in color now. These drifters spent time, and I have all the statistics and timings and everything, but it's way too long to go into for that, so you'll just have to listen to the qualitative narrative here. These were meandering around in the northern Sargasso Sea before the NAO wind anomaly began in December 2009. They lost their drogues and then rapidly moved to the east almost to Gibraltar. When the wind anomaly ceased by the end of March 2010, that's almost, with each one, it's almost precisely when they turned south with the prevailing winds and currents and ran aground shortly thereafter. It's like the wind turned off and reverted right back. You saw those time series almost instantly, it looks like, in those, you know. But anyway, those had gone too far east. And when they made their turn, that was it. That was the end for them. And there were anecdotal observations of Sargassum beaching on Morocco also. And then no observations down there because it's just south of there. It's a desert area and there were probably no people. It may well have happened, but nobody would have seen it. And then there were lots of observations as you're coming around the corner of Africa and down in there. So, but those ones just kind of went too far and weren't able to make the turn. The next group also began in the northern Sargasso Sea, were also blown rapidly to the east by the anomalous winds, and then also turned to the south when the winds turned off. However, they were farther offshore when they made their turn, and they were able to join the westward NEC to eventually arrive and ground at 3 different sites in the eastern and north central Caribbean during the Sargassum inundations of 2011, sort of precisely. So now we've moved along in our story. We have drifters that were clearly in the Sargasso Sea, lost their drogues, made a turn, and beached there in various countries. One, the Dominican Republic, and one of the islands in the northeast, and then down in the southeastern Caribbean. The next set were actually deployed over there in the Canary Current, but you can almost see from the gray trajectories, and then they're around the same time as that whole thing was happening. They probably came from the Sargasso Sea, also from the subtropical gyre. They were deployed there between 20 and 25 north around the same time period of the previous drifters, and also made eastward trips across the North Atlantic to arrive in the southern Bahamas, eastern Cuba, and the southeastern Caribbean in 2011 during the Sargassum inundations, all going up on the beaches. And these illustrate pathways from the north side of the Giddy Dome that I was talking about, and from the eastern equatorial Atlantic, both grounding in 2011 on the African coast there where the red dots are. I forgot to say that part, but it probably was obvious. Around the time that the inundations were being reported there. So most importantly, I would say, is the green one there that shows connectivity, potential connectivity. These particular drifters did not do it, but in the previous statistical drifter maps, and sort of you just know that some of the drifters did that. I was only looking at the 2008 to 2015 time period in the drifter database. It's a vast database, and I was just so. And then these drifters show pathways from the tropical Atlantic, wherever they came from, that made the closest approaches to Brazil during the whole thing. That was the last other place that the Sargassum was observed. Made very close approaches to the equatorial area of Brazil, and then westward to ground in or near the Caribbean in 2011 also. These are all different drifters. It was a real hot spot for grounding in the Caribbean during 2011. These illustrate how Sargassum could have possibly arrived to Brazil at the right time due to the recirculating tropical Atlantic currents. It didn't arrive by the green one, but the other two are caught up in the region that has the back and forth current area. And this was all of them again that we just looked at, illustrating various aspects of the circulation under the effects of windage, as most had lost their drifters relatively early on in their journeys. So you can sort of get an idea of what we're talking about here. Now we'll get to the HICOM results. Drifters are useful for showing many aspects of the circulation, but because they are limited in number and lifespan, they cannot be used to demonstrate interannual variability, such as that due to the 2009-2010 NAO wind event. A data assimilating numerical model can add this capability. First, the results from the combined time period will be shown for no windage and 1% windage, followed by a time series of the likelihood of the two selected pathways that I show. Okay, this Nathan Putman helped with the running of the HICOM thing, of the HICOM model, and give me the results. 30,000 particles were seeded in the Caribbean Sea during April, May, June of each year from 2008 to 2015 and backtracked for 3 years. 1 year back, year 1 locations are shown in red, year 2 is in blue, and year 3 is in green. Results are for no windage left panel and 1% windage right panel. You can see they're different. The most striking difference is how many more particles originate north of 20 for the 1% windage case, especially in the northeastern Atlantic. The tropical and South Atlantic parts of the domain are approximately the same, at least to me by eye. I ran some numbers on them, but it wasn't relevant to this particular talk. So the most striking difference is how many more particles originate. Yeah. The tropical and South Atlantic parts of the domain are approximately the same. There's also significantly more input to the Caribbean from the western subtropical gyre area for the 1% windage case than for the no windage case. The red means it's going into the Caribbean in 1 year or less. So you can see where it all comes from on the short term. And if you look closely, you can see that in the windage case, the red 1 year track goes all the way up to about 30, or in some cases a little higher out in this. And those are the ones that were the fast track, where the drifters went straight in kind of, and then the other ones take longer to get into the recirculating tropical circulation, although there's another fast track coming straight from the South Atlantic up there too, a 1 year track. Then I did an experiment in which I devised 2 pathways that would kind of get at what I wanted to know about this. From the same run that you just saw, this is I selected HICOM particles that matched a prescribed pathway number 1. And again, it's the, no windage on the left and windage on the right, where during year 3, it's the same. The particles were required to be north of 20 north and east of 80 west, green. And during year 2, it was the opposite of the second one I'm going to do. Oh, I said the same because I'm talking about both pathways. This is pathway number 1. 3 years back, it had to be up in the north of 20. 2 years back, it just had to be east of 30 west, so that we could examine the Gibraltar Canary Current connection, the Africa thing, and test that all out. And then the 1 year particles were just left alone, and whatever met those year 3 and year 2 criteria was kept in. This pathway was chosen in order to focus on the eastern Atlantic, from the Sargassum Sea to Gibraltar and the Canary Current. There are far more particles participating in pathway number 1 for the 1% windage case than for the no windage case. There are also more that have made it southward in the Canary Current around the Guinea Dome. It's these red ones down here now in the tropics, and eastward into the Gulf of Guinea, all the way to right into the end of the Gulf of Guinea there, followed by rapid transit across the tropical Atlantic to the Caribbean within 1 year. And I know this because they're red. So that's what HICOM is showing for that. And pathway number 2, I just wanted to examine another scenario here. All the particles that matched pathway 2, during year 3, it was the same requirement, north of 20 and east of 80. During year 2, you had to be on the other side of 30 west, eliminate that whole other first pathway. And again, the year 1 had no constraint. This pathway was chosen to focus on the western Atlantic from the Sargasso Sea southward into the Caribbean Sea. Now, with that strong eastward wind anomaly, windage shows that, but the Ekman flow, of course, would be Ekman flow, which was added to the windage from the NSEP velocities, and it's presumably in the drifter trajectories, would have given it a pathway to 45 to the whole transport 90 degrees to the right. And so wouldn't that have increased flow into the Caribbean through the northern Caribbean passages, possibly? So I wanted to look at that. Fewer particles take pathway number 2 for either the 1% windage or no windage cases than for pathway number 1. However, there are many more for the 1% windage case. These particles represent a pathway where they recirculate in the subtropical gyre for 3 years or more, but green is 3 years ago, until they finally enter the Caribbean from either the east or directly from the north, because they have enough time in 3 years to make several circuits of the Sargassum, the subtropical gyre. So they either, in this analysis, yes, these are, I think I may have forgotten to say that the initial seeding and then 1 year back in June, on June 1st, they were seeded in April, May, June. 1 year back was the red particles on June 1st, where they were. 2 years back was on June 1st, and then 3 years back was also on June 1st. And this is then finally got to a little interannual variability. This is a time series by year of each year. The year represents the year that the Caribbean year, where particles made it to the Caribbean. And so you can see that what stands out, first of all, is 2011 is a special year in the Caribbean. Now, this is an annual time series. In the cases of no windage, the green and purple lines down at the bottom, with no windage, few particles follow either pathway, 1 or 2, as almost all of the no windage input to the Caribbean originates south of 20 north. However, in the cases of 1% windage, the red and blue lines, where red is pathway 1 and blue is pathway number 2, the most particles follow each path during Caribbean year 2011. For pathway number 1, the cause of this is the eastward wind anomaly caused by the NAO. And for pathway number 2, the cause is likely direct southward Ekman transport, also caused by the eastward NAO wind anomaly. That pathway just opened up more robustly during the... And these are the same drifter thing. These are the same ones we talked about. They illustrate the possible routes leading to the tropical Atlantic and Caribbean Sea. The input from the north, greater than 20 north, is only present significantly when windage is considered, NSEP and HICOM with 1% windage, and the undrogue drifters. You remember, all 3 of those were saying the same thing about with the addition of windage, you have a northern input, and without, you have very little there. That also explains why long ago at the beginning there, and the early studies of the Sargassum event, when they used only drogue drifters and only HICOM with no windage correction, it didn't show any input from the north at all. That's how they concluded that the source region was the tropical Atlantic or maybe the South Atlantic. You could conclude that too if you only looked at those maps. So the input from the north is only present significantly when windage is considered. However, it is present in all years. So that is a pathway of water flow in all years with the windage or with the, undrogue drifters. It's a pathway. The arrival of Sargassum to the Caribbean during 2011, we already said it was caused by the NAO eastward wind anomaly, kind of extending the Sargasso Sea east to the Gibraltar-Morocco region, so that the Sargassum could enter this present pathway that's there every year, but not every year do you have Sargassum in it. And the undrogue drifters demonstrated that graphically when they crashed into the coast and everything in a place they don't normally ground as much. All right, we're done. We only have one conclusion slide. Sargassum is not usually found in the Caribbean and tropical Atlantic, but it has been there in great quantities starting in 2011. I'd like to elaborate on that for 1 second. So it got to the tropics where the conditions are completely different. It's a growing plant, and it spends its entire life pelagic, but it grows by breaking and growing and everything, and clumping together and propagation. And it's a plant, and it had been confined in the Sargasso Sea with the very low nutrient conditions and different temperatures. So now it's got warm temperatures, higher nutrients, and areas just like the center of the Sargasso Sea of convergence and recirculation. There's an important one over underneath Africa there, where drifters and things tend to converge and hang around for a while before taking the route across the ocean. And there's another one, the North Brazil current retroflexion and rings area is another area that some studies have shown. A recent paper by Nathan Putman has shown this, that it's another pathway, where a delayed pathway, and then there's direct pathways too into the Caribbean. So it's been growing and propagating and getting worse and worse, and 2018 was the worst year yet. And the other wrinkle in this whole thing was that in 2014, people in Woods Hole who've been measuring actual sargassum and typing it into subspecies discovered that the one that was blooming the most and making just absolutely outperforming every other kind was this subspecies, Sargassum natans 8, whereas the sargassum in the Sargassum Sea is fluitans 3 and natans 1. It's a fine thing, but they do genetic studies, and they could tell us. Now, the first guy to study Sargassum par in 1937 noticed there was a certain small amount of natans 8 also up in the Caribbean, but also up in the Sargasso Sea. So biologists are working hard on this and trying to figure out what is all that, where did the natans 8 come from? And so there's a whole new kind that's mixed in with the regular kind, now all growing in place and circulating in the currents. And so that's why 2018 could be the biggest year yet, and who knows, it's hard to predict. On physical grounds alone, you would predict that everything would clear out of there eventually, but what do you do when you have to look into models that have growth? So sargassum is likely to be affected by windage at the sea surface. I think we know that. We show how when windage is taken into consideration, the surface circulation of the Atlantic is different in several key ways than it is when windage is not included. And the pathway from the Atlantic north of 20 into the Caribbean is present at all years when windage is included. However, the NAO wind anomaly allowed the sargassum to escape the Sargasso Sea to the east, where it could then move southwest directly to the Caribbean, and also south in the Canary Current to the tropical Atlantic, and affect the coasts of equatorial Africa and Brazil, and later the Caribbean Sea, as observed. And one last point is that I didn't show it because I didn't need it for this particular wind talk, but I have all the sargassum data from the Woods Hole people who I've sort of made friends with, and we can show that the kind that was present before 2014 in the tropical Atlantic and Caribbean was indeed the blend of those two subspecies that have been for decades and decades and decades classic. That mix says Sargasso Sea, basically, when it's that blend. And that blend is what came in 2011. But by 2014, it morphed a little bit. But it was there in 2011. And it was also that mix of the two subspecies was what was observed off Africa and Brazil and in the Caribbean. So we feel pretty confident that this story is at least this one, I think, actually might be more plausible than that the sargassum suddenly came in 2011 from places that nobody's ever seen sargassum before. So that's about all that I'm going to say about that. What did I do wrong here? Oh, I'm going sideways. There we go. I put the side arrow. I didn't even know that did anything. Thank you.